welcome guys. So this video, let's talk about Cantor intersection theorem. So before I start, please subscribe to my channel, and you can also check my playlist. I will leave below. Basically, this is a real analysis playlist. I prove a lot of really amazing theorem in real analysis, and I will prepare a lecture and basically like a systematic arrange the structure. Okay, yeah, but the Cantor theorem just say that it's really also important theorem in like the advanced calculus. So let me just go into it and prove. And before I start, hopefully you guys subscribe to my channel and click the like button below. Okay. Okay, so the Cantor intersection theorem is basically not only restricted to Rn. Basically, if you have a X basic topological space or what, you have a metric. So any metric space. So any space you want, you can define distance. Then you can define what compact means, right? So compact means that any finite open cover has finite subcover. So this theorem says that you have K1, K2 up to Kn, and you keep going, right? So there's a infinite compact sets which one is contained in the previous one, and the OKI are compact, so and also non-empty. So theorem says that your intersection of it will be non-empty. So this says yeah, so this is the intersection theorem. The result will be non-empty. It's obviously that the result can be a point, right? If you think that you have a closed interval and that interval keeps shrinking, right? And finally, then it will contain a point. Okay, but how to prove it? So this kind of theorem usually hard to prove. The reason is that they are not in a n-dimensional Euclidean space. So we don't have a clear picture. So all we need to do is that we write down everything we know in the topology, and then we try to use the definition. Okay. So let's consider K1D as a subspace, right? Actually, it doesn't matter. Okay. So let Vn to be K1 divided by Kn. So not that I should not say divide, but I should say delete. So x belongs to K1, x do not belong to Kn. It's open in K1, and the reason is that yeah, two closed set, right? So this guy is K1, and that is the first ring is K1 delete K2, right? And then the second ring will be K1 divided by K3. Right? Okay, so let's assume that let's assume that all the intersections are actually empty. Okay. So let's define Fn to be Vn n from 1, keep going, right? So obviously F covers K1. The reason is that if you union all this Fvn, then you get the union of K1 delete Kn, right? And by default, the simple case theory is K1 delete all the intersection of Kn, right? And since they are empty, so you delete the empty is K1, right? So cover K1. But now the problem is that K1 is compact, right? So obviously that you can find what? You can find a finite cover, right? So there's a V1 up to V2. So now you have V, and we also have V1 subset of V2, V3, right? Because it keep deleting a small part. So since K1 is compact, right? So I can write down the finite subcover. So I can label the first is 1, the final is X. So Vx will be larger than everything. Vx will cover everything, right? So Vx will cover everything, right? So Vx, I from 1 to x, Vi, right, will be Vx, and it will equals to K1. Okay, it will equals to K1. But by definition, how about Kx, right? How about I should say Vx. Sorry, let me change the notation. Yeah, we got a little notation problem, but it's can be fixed quickly. So right, so how about this Vx? So right, so this is from definition we know that now Vx equals to K1 equals to I from 1 to x because K1 is compact, right? So this Kx, right? Yes, correct, Kx. So this Vx is K1 delete Kx, right? So K1 delete K1 delete Kx will be Kx, right? So Kx will be K1 delete Vx, right? This guy is Vx, but Vx is equals to K1, right? So Kx is empty, right? But my assumption is that everything is non-empty, so contradiction. Okay, yeah, that's a proof. Very nice, right? So very simple theorem. Yeah, so yeah, it's a very short theorem. And the next time, we will prove that the sequentially compact and compact general metric space, and I think seldom people talk about it. Okay, I will see you guys in the next videos.